I'm Bill Kinney, and this is my 9th video on multivariable calculus challenge problems. This one's going to be different than most of the ones we've done so far. Usually we are taking a problem, solving it by hand, and using the computer program that you see here, Mathematica, to visualize what's going on in the problem. Here in this video we're going entirely in Mathematica, but don't leave. Even if you don't have Mathematica, I think it'll definitely be worth your while to stick with this because you're going to see some pretty cool things that hopefully will help you understand multivariable calculus better. We are taking problems from Rogawski Adams calculus book, 3rd edition, but most calculus books have problems very similar to what we're doing, so it's worthwhile even if you have some other calculus book. In this video we're looking at problem 14 in section 11.2 of that book, though I'm modifying this problem quite a bit. The problem 14 in that section is stated much more simply. It says take this parametric curve that I've highlighted here, c of t equals cosine of 5t, that's the x-coordinate, comma sine of 3t, that's the y-coordinate, and the problem says just use some sort of computer algebra system, either Mathematica or MATLAB or maybe even your calculator, to approximate the arc length of the curve this generates as t varies from 0 to 2 pi. I'm going to do much more in this video, and I have really an ulterior motive besides just solving the problem. I want to illustrate some ideas that are pretty important if you're going to understand the idea of arc length or distance traveled and its relationship to speed. So we're going to use the program you see here, Mathematica, in part A to make an animation of the motion. Again, you don't have to have Mathematica to appreciate what you're going to see. You can focus more on the big ideas if you don't have Mathematica. If you do have Mathematica, you could pause the video, write down the code, and use the code to experiment on your own. So we'll just make an animation to see what the motion is like. It's something called a Lissajous curve. It's very pretty curve actually, very interesting. Part B, I'm going to do something that I think is pretty significant. I'm going to make functions and summations in Mathematica. I know this statement's kind of vague. To estimate the distance traveled or arc length along this parametric curve as t goes from 0 to 2 pi. In the videos up to this point, when I've talked about distance traveled and speed, I've treated it intuitively. I've said, okay, the speed is something that's going to give you the length of something called the velocity vector. We're not into vectors officially in Rogawski Adams' book until chapter 12, but I like introducing them early. And then I said that the distance traveled is the integral of the speed. Kind of an intuitive thing that has definitely analogs back even in a first semester of calculus. All right, here I want to approach it differently, more like most books do when they talk about arc length. So you may want to read a section about arc length before coming back to what I show you here, or maybe you want to watch this first before you go ahead and read a section about arc length. We're going to approach this from the idea of a Riemann sum. In part C, I'm going to ultimately use a built-in Mathematica command called NIntegrate to estimate that distance traveled and get the best possible answer for the problem itself as far as that arc length goes. But I also want to talk about how to translate the idea in part B to an integral we can actually do in part C. Part D is kind of a nice add-on, just talking about numerical integration methods. If you don't care about numerical integration methods, maybe this is a part you could skip. I'll talk about left-hand sums, right-hand sums, trapezoid rule, midpoint rule, and Simpson's rule. In doing it, implementing those in Mathematica, I'm going to use something that I call an empirical approach that can be found in the calculus text by Hughes-Hallett, Gleason, McCallum et al., which is not the most common thing to do. I'll talk about that as I get there. Parts E and F are to summarize everything. We're going to find the speed function using the fundamental theorem of calculus in part E, really justifying our approach to the speed function that we've used previously. Part F, we will graph the speed and distance traveled functions and use Mathematica to approximate maximum and minimum speeds, and at least one moment in time where those max and mins occur. All right, now we're on to actually seeing what happens here. Here is Mathematica Code that can define the functions. This is x as a function of time, cosine of 5t. This is y as a function of time, sine of 3t. This is the point, c of t itself, f of t comma g of t. This is its velocity vector, and this is its acceleration vector. I can enter those functions. They are now entered, and we can enjoy the animation. And I did add vectors to the picture because it does enrich what we see here. So we see this motion along this blue curve that is being drawn. Very interesting kind of a motion. You can imagine the black dot is the object that's moving. Maybe it's a car and you are driving this car around in this curve that you see here. What are these arrows? The blue arrow that points from the origin to the black dot is called the position vector. It's just essentially keeping track of where the object is. The red arrow is called the velocity vector. It's the derivative of the position vector, whatever that might mean. We'll have to get into that much later. It's somehow measuring the rate of change of the blue vector. Actually, I'm lying a little bit. It's not quite the velocity vector. It's half as long. If I did the velocity vector itself, it would be too long. It's always pointing tangent to the curve. At any moment in time, it's pointing in the direction of motion at that instant in time. If you're in the car, it's at that moment in time, it's the direction you're looking at. I just snapped my fingers there. All right, and the orange vector is the acceleration vector. Actually, it's the acceleration vector divided by 10. It's 10 times shorter than the actual acceleration vector. It's somehow measuring the rate of change of the velocity vector. One thing to notice here that I mentioned before is that when the angle between the orange and red vectors is less than 90 degrees, the red vector is getting longer. You're speeding up. And when the angle is greater than 90 degrees, then the red vector is getting shorter. You're slowing down. And you can see that if you look carefully at the animation here. Okay, so there is the motion. Very pretty curve, very interesting kind of motion. You're definitely speeding up and slowing down. There's definitely some sort of max speed and min speed, and maybe somewhat intuitively, you're speeding up in the straightaways and slowing down in the curves, just like you'd actually have to do in a car. All right, now we're on to part B. Before I talk about what you see here, which is a bit confusing, let's look at an animation. Actually, I'm going to have to go back out again. So here's the finished Lissajous curve. So now we're not focused on the motion itself so much as the curve. And again, remember the main goal of the problem, as stated in the book, was to just find the arc length of this curve. How far does the dot travel along the curve as time goes from 0 to 2 pi? And the approach that's typically taken in deriving the formula for arc length in textbooks is to try to approximate this curve with what's called a polygonal curve. For example, here's a polygonal curve, a square, that is supposed to be a very rough approximation of this curve. You can notice the vertices of the square are at points along the curve. We are connecting those vertices with line segments, and the idea is you can approximate the total length of the curve by adding up the distances along these line segments. Now again, this is not doing a very good job. Very poor approximation, but as I continue increasing the number n here, which sometimes gives you a simple picture and sometimes gives you a complicated picture for reasons I won't go into, sometimes gives you a very pretty picture like that one when n is 8, we are getting better and better approximations to the curve because we are sampling more points along the curve and connecting those sample points with straight line segments. And once you get to about n equals, I think maybe 16 or so, it starts to get to be a fairly decent approximation to the curve. Okay, this is not too bad looking here. It doesn't consistently get better. This one looks worse now. But generally speaking, on average, as n gets larger and larger, we're getting better approximations to the curve. Once n is up to around 30 or 35 or so, now we're getting pretty close. Okay, so we can find the distance along each of these line segments, add up those distances to get a total approximation of the curve. What does k do? K just shows you the dots that we're connecting here along that curve with those straight line segments, okay, for any different value of n. Once n is the highest possible value there, you can hardly tell the difference between the red line segments and the blue curve. We are sampling lots of points here, 100 points along the curve. Okay, so that's supposed to be motivation for trying to understand what I'm saying here in red. Thinking in terms of how you approach integration initially. You always have your interval that you partition into sub-intervals, n sub-intervals. A is the left endpoint, 0, B is the right endpoint, 2 pi. The length of each of these sub-intervals, delta t, is b minus a over n, which is 2 pi over n. t sub k represents really the right endpoint of the kth subinterval. If k was 3, then it would be the right endpoint of the third subinterval. Here's the formula for that. And we are approximating the total distance traveled, or arc length, by, again, adding up distances along line segments. CTK minus 1 is a black dot. CTK is the next black dot in the animation. Dist stands for distance, and using the Pythagorean theorem, or alternatively the distance formula, this square root does give you those distances along those line segments, and we're adding them up. I'm getting Mathematica with this code that you see right here to actually implement what we see here as an approximation. I call it dist_approx as a function of n. And down here I can see the output for that in table form. So as n goes from 0 to 20, or 1 to 20 down this column here, we can see the distance approximation. Hopefully get better and better to the total best approximation to the length of the curve as t goes from 0 to 2 pi. You can also make an animation of this. I'm letting n go all the way up to 1,000 here in the animation. When n is 42, our approximation to the arc length is 24.2076. Let n keep going higher and higher. The computation bogs down a little bit, but once n is up to 1,000, we're getting 24.602 as the approximation we get with this approach. Okay, 24.602. How close is that? Well, ignore this for the moment. This code gives us the best approximation to 3 places after the decimal, 24.603, NIntegrate. You can see we got 24.602 there. Mathematica is doing NIntegrate, integrating this function to give us the best approximation with some sort of internal scheme. But how do you go from what we did up here, doing an approximation like this, to actually doing an integral? You know, how are they related? Well, this is sort of a pseudo-justification for what I'm saying down here to do the integral to get the total distance traveled. It's not really fully rigorous, but bear with me here. For a given small positive value of delta t, we can say the following is true. Now that's an approximately equal to symbol, so this is why it's kind of not real rigorous. We can say this square root equals this, including the delta t here that's outside the square root. Now why would these two things be equal? Well, if you think of delta t here, which is positive, as being the square root of delta t squared, and merge the square roots together, you see we've got delta t's in the denominators of these two fractions that are being squared. And so these two things would equal. The delta t's would cancel. But this thing, well, that can be well approximated, at least if delta t is small, in terms of derivatives. Look what we've got there, derivatives in there, dx dt and dy dt evaluated at t sub k minus 1. These really are difference quotients. They approximate derivatives for the functions f and g, which remember are giving the x and y coordinates as functions of time for the curve. These are their derivatives. We're replacing these difference quotients with their derivatives. And the reason we're doing that is because now this looks like a function that could be integrated, and in fact that is what we end up doing. We integrate that function. The total distance could be approximation by a sum like this. This should look like a Riemann sum. If you know about Riemann sums for this function over this interval, letting delta t go to 0, it leads us to say it makes sense to essentially define the total distance by this integral. Okay, so again, this is not a fully rigorous derivation, but hopefully this makes some intuitive sense to you. The goal being to justify using NIntegrate for this function. We are integrating this function, the square root of the sum of the squares of the derivatives, which is the speed, as I've talked about in previous videos, over the interval from 0 to 2 pi. 24.603, again, would be our best approximation for the arc length or distance traveled along the curve. Now, here's the part maybe you want to skip and go ahead to later in the video. I'm going to briefly talk about numerical integration techniques in Mathematica. It's still important. And just show you can program it pretty easily. You can use a summation button actually on this writing assistant. There's a summation button here. Oops, where'd that go? There we go. This button right here can make summations like that, and you can use summations to essentially define a left-hand sum, a right-hand sum, and hopefully looking at the summation it makes sense. By the way, this t of kn is really t sub k. Okay, so the notation could be a little confusing. But if you learn about left and right-hand approximations of integrals, hopefully these summations make sense based on that. And this is a midpoint sum down here. Notice this is really the average of t sub k minus 1 and t sub k that I'm plugging into the function that I'm integrating. By the way, again, the function we're integrating is not f or g, but the square root of f prime squared plus g prime squared. That's why the thing we're adding is a little strange. As far as the trapezoid rule and Simpson's rule goes, this is where I'm talking about with the empirical approach. Turns out the trapezoid rule is the average of the left and right-hand sums. Many books don't approach the trapezoid rule that way. They approach it more from adding up areas of trapezoids. That is equivalent to this. And the empirical approach also says Simpson's rule can be thought of as a weighted average of the midpoint rule and the trapezoid rule, where you give the midpoint rule twice the weight as the trapezoid rule. This is based on an empirical approach, meaning where you use technology to make estimates of these things, for example with the midpoint rule and trapezoid rule, and you typically see that at least for large values of n, the midpoint sum does about twice as good as the trapezoid sum does, for example, and that's why you give it twice the weight. Anyway, entering this code into Mathematica will allow us to now calculate the values of these things. I'm letting n go from 10 to 100 here, and we see the left-hand sums, right-hand sums, trapezoid sums, midpoint sums, and Simpson's rule. And you can see Simpson's rule definitely does the best, although they're all not doing too bad here. You know, again, the closest answer is 24.603. Simpson's rule is definitely getting there most quickly, but they're all not doing too bad even when n is 30 or so. So that's just interesting to see. And again, we compare it with what NIntegrate produces, 24.603. All right, now we're on to the part E. And if you skipped ahead, this is the part to skip ahead to, and hopefully you could find it. What was the goal in part E? The goal is to find the speed function. So now, again, I was approaching the speed function intuitively before. Now we're being a little bit more rigorous once we have the distance traveled. Thinking of the distance traveled from time 0 to time t, we can think of it as an integral, like I have up here. Except now think of the end point for time as being a variable. And that's why I put t up in the upper limit of the integral here. That's the variable for this function. Technically speaking, you should call the variable for the integrand something else. If you look closely, this is not a t here, this is a tau. This integral is giving you the distance traveled function. And it is an integral of the speed, and the reason now is really the fundamental theorem of calculus. If I differentiate this thing, the speed function is ds dt, is dis prime of t. When you differentiate an integral like this, you get rid of the integral sign and you just have the integrand. And now you go back to having t as the variable, because we are differentiating with respect to t, ultimately. If that was confusing to you, you'll want to review the fundamental theorem of calculus. Sometimes it's called the second fundamental theorem of calculus, what I'm saying here. Anyway, this is justifying that the speed function is given by this formula, and we can plug it in Mathematica and see what it ends up equaling. It ends up equaling this. This is something that can't really be simplified anymore because the frequencies here, the coefficients of t inside the cosine and sine are different. So we can't, and you know, the coefficients out in front are different as well. So we can't use any trigonometric identities, evidently, to simplify this very much. But this is just what the speed function is. Now we're on to the last part of the problem. We are going to use NIntegrate again, but now with a variable instead of a fixed 2 pi at the end here, to define our distance traveled function to help us now plot both the distance and the speed functions. It takes a few seconds here because it's doing a lot of numerical integrations. And there we go, the distance traveled is in blue and the speed is in red. The speed is always positive, but it's going up and down, which should make sense. The motion for the Lissajous curve was speeding up and slowing down a lot. The distance traveled function has to always be increasing because the speed, its derivative, is always positive. So this blue graph's always going up, but it is sometimes concave up when you're speeding up and sometimes concave down when you're slowing down. Looks like if you glance over this red curve, the speed is maybe maximized close to 1, for example, and also close to maybe 2.2 and 4.1 or so, and minimized near 0.6 or so, and maybe 2.5 or so, etc. If you differentiate the speed, set that derivative equal to 0 and solve for t, you can try to figure out what those maxes and mins are. And by the way, the derivative of the speed is not the acceleration or the length of the acceleration vector. Don't make that mistake of thinking that's the case here. We will see eventually that they are different things. Anyway, here the derivative of the speed is that. It's kind of complicated. Does it simplify? Well, if you use trig reduce here, it does simplify a little bit. But still, setting that equal to 0 and trying to solve for t by hand looks like it probably would be a pain. It's probably better to use technology, find root of Mathematica, giving an initial guess of 1 will try to help us find that maximum. T equals 0.953966 is the value of t where you have this high point up there. And the speed there is approximately 5.76. That is the max height here. 5.76 units of distance per unit of time. And minimized near t equals 0.6 down there, and so giving a guess close to 0.6 using find root gives us a t location of about 0.6168. Plugging that into the speed function gives us a minimum speed of about 0.8765. That is the minimum value here approximately that we see. Okay, so illustrating other things you can do with Mathematica symbolically to try to find estimates for those things. So I hope you got a lot out of this even if you don't have Mathematica. These ideas are really important as we go forward in multivariable calculus.